So this is how I'm going to, schedule my presentation. I would like to first discuss about Fujitsu's journey in processor technology and supercomputing domain. Then I'd be talking about how our, in spite of contributing to varied ecosystem, my team is sending some messages. Just a second, I can't read it here because it's shared. Now it's fine. Okay. They were actually telling me that it is not in presenter mode. Okay. So, so this basically connects our vision towards supporting varied ecosystem along with AI for science. And then I'll be talking about scientific ML and AI surrogate modeling, how it includes the complete ecosystem of development of surrogate model, evaluation methods, trade-offs, and benchmarks. And of course, because this is a oneAPI summit, so I would like to connect what we are doing in scientific ML with the way we can leverage the power of oneDNN. And here, because in the past, we have spoken about how we have enabled oneDAL for our ARM ecosystem, and the Fujitsu team has been contributing to oneDNN for many years now. So I would like to connect the two scopes together. And then just after me, I will have presentation from two of my team members, Ashish and Shreyas, who would be talking more details on how we are contributing to oneDNN, where scientific ML won't be the focus area. So basically, that is overall, scope of the talk that we have planned for today. This slide, I'm sure you might be knowing about Fujitsu's journey in the processor technology and supercomputing domain. We have been contributing to this for over 70 years now. The latest project that we are contributing is FUJITSU-MONAKA, which is our 2 nanometer ARM chip. And of course, there are other announcements of Monaka X and subsequently other projects as well. I'll just limit my discussion to Monaka for today. This is something that introduces us, and we have spoken about this on other forums as well. So this is our the basic specification of our 2 nanometer ARM chips. As you can see, this chip is going to house two sockets of 144 cores each, which is like 288 cores per node. And apart from that, this will also be the first ARM chip to have confidential computing on chip, right, in the hardware. And our team is also contributing towards adding, towards developing the software stack for confidential computing. And many of these collaborations are with ARM. Okay, so this is a broader snapshot of different areas in which we are developing majorly from open source perspective. As you can see right from the bottom, the software stack of Monaka is going to house various kinds of software libraries, which has been enabled, tuned, and accelerated for ARM ecosystem. This includes our contributions at OS level, then the file system related improvisations, tool chains related to what we have contributed in these ecosystem. And but my team majorly works for the AI software frameworks, right? And in this, there are various domains for which we have enabled the software stacks for ARM ecosystem, enabled, tuned, enabled and accelerated both. This majorly includes the machine learning stack, the deep learning LLM stack, data variety of data platforms, and confidential computing architecture as well. And in all this, we are open to collaborations from international community, and oneAPI is definitely an important stack on which we have contributed, and we are using it at various levels. This is again our journey in OSS community, right? So I'm happy to say that not just with Fujitsu-MONAKA, Fujitsu has contributed to OSS community for a very long time now, right from how we contributed to Linux kernel for mission critical server in 2005 to KVM virtualization in 2010. Then OpenStack and Kubernetes in 2018 to how we ported oneDNN to ARM for the first time in 2021, and this stack was used in Fugaku. And thereafter, contributions to automotive grade Linux, Yocto, ARM Linux on supercomputer Fugaku. And then last year, we spoke at length about how we have ported OneDAL for ARM. And likewise, there are other developments that we have been involved in 2025, that is the current year. Now, let me slowly, okay, I'll just close my video for some time to avoid any network issue. Okay, so this is now before I go and discuss about details of oneDNN and the oneAPI stack, I would like to bring our everyone's focus to AI for science. And in fact, we were also thinking that in most of these oneAPI Dev Summit, we have focused majorly on the contributions to these stacks. And this year, the UXL committee was also trying to bring in a flavor of how oneDNN can be, or the power of oneDNN can be leveraged to solve problems in different domains. And that is why I picked AI for science as one of the theme, because this also is an important theme in which we contribute. Now, to give an idea of what do we mean by AI for science, I have the two lines which is mentioned at the top. So AI for science spans across a broad umbrella that combines AI and ML techniques with scientific discovery, where simulations, experiments, and data analytics are the major key drivers of cutting-edge discoveries. And when we say AI for science, it includes varied domains, as you can see. And I think each one of us can connect to one or many of these domains. And we might have definitely been a part of this ecosystem at some time in our professional journey or even now. So when you talk about physics, AI for science might apply to computational fluid dynamics or quantum mechanics, plasma physics, and things like that. So and then likewise, for climate science, biology, chemistry, and all these domains. Now, what if you see this diagram? It basically connects the AI for science and shows how the lower bottom is the AI framework, which we are trying to enable and accelerate for ARM ecosystem, and how this particular work can be leveraged to use AI for science, right? And what do we essentially mean by this? Of course, I mean, symbolically, this figure looks like quite natural for us to accept, but then in the next subsequent slides, I'm going to technically, deep dive into how are these two ecosystems actually connected, right? So let me move on to the next slide. Okay. Now, if you see this slide, this slide basically highlights how AI surrogate models are emerging as a new computational paradigm for science and engineering. And instead of relying solely on traditional HPC simulations, which are accurate but extremely compute intensive, AI surrogates are known to deliver, or have been seen to deliver, faster and learned approximations in lesser time, which means learned approximation in lesser time. So we see two key application domains here that I would like to focus on majorly. The first is structural analysis, where problems like Hertz contact stress require very high compute for nonlinear mechanics, and surrogate might help to reduce the cost. And likewise, the other domain that I would like to bring into your focus is computational fluid dynamics, where we can say that Navier-Stokes solvers are powerful, but they are again known to be computationally heavy. So AI surrogate can bring in speed and scalability benefits to this domain. And then finally, you can see an example case study at the bottom where we are citing work of Wendell and Klein, previous work of Wendell and Klein, where they are using 3D CNNs for fluid dynamics, and the figure also shows how AI surrogate help them improve speed, accuracy, and generalization, even for complex simulations like submarine flow. So the key message here is AI surrogates don't just replace physics, but they augment HPC by providing faster, scalable approximations that open new possibilities. Now, with this, I would like to go to the next slide, which is titled as HPC versus AI surrogate evaluation methodology. Now, this slide basically compares HPC simulations with AI surrogate model. And the core challenge, if you see, the core challenge here is that while HPC delivers very high accuracy, it is extremely time and resource intensive, and you can see the graphical representation at the lower bottom of the screen, where AI surrogate promises a much faster result. When you see the comparison of accuracy and performance on side by side. Now, on execution time, AI surrogates can also reduce runtime from thousands of seconds to near real time, which is enabling much faster scientific iteration. At the kernel level, as we know, at kernel level, the performance tuning is a critical task, right? So, on ARM CPUs, a few kernels dominate runtime and optimizing them with frameworks like oneDNN, and this is what can be leveraged to get major speedups, and that is what I would like to discuss in the session today. So finally, on accuracy, while training ML or pins show higher errors, the advanced pin and newer AI approaches are bridging this gap, and bridging this gap, and there's a lot of work that needs to be done here still. So that is why I've just mentioned symbolically that the arrow that you see out here is the scope of global R&D and collaboration. How do we accelerate it further and match up with the accuracy that HPC can solve? So it's like striking a balance between speed and accuracy. Like, you are of course being able to do it faster, but at the same time, how we can leverage these stacks to also improve the accuracy while doing it faster. Now, with this background, in the next two slides, I would like to discuss how our team has contributed to solving this problem. And that's why the title of this slide basically says how we have contributed in PyTorch OSS for AI surrogate. Now, when we look at the performance bottlenecks in PyTorch-based AI surrogates, especially for graph neural network and GCN, which is graph convolutional network models, one kernel we observed that as you can see in the pull request image that we have pasted here. So with this study, with this development, we found that one kernel, which is the scatter gather kernel, used to take up nearly 63% of the inference time, and that is what is represented here. The reason for this was that FBGEM, which is a critical library for matrix multiplication, wasn't enabled for ARM CPU, and that is what was creating a scalability challenge. So when our team at Fujitsu stepped in to identify this problem, we basically, to solve this, we contributed an optimized gather kernel directly to PyTorch open source. And now this is fully integrated with PyTorch and PyTorch geometric stack. So the result that we got here was significant, which means that at primitive function level, we achieved about 2.9x speed up. And at benchmark level, we got almost 16 percentage reduction in the execution time. And that is what is exemplified over here. So what you see at the bottom basically mentions how we basically implemented this kernel, and at the same time we achieved a speed up of 2.9x and at benchmark level and overall 16% reduction in the execution time. So the impact here that I would like to bring in your attention to, the impact that we were able to create here can be basically exemplified in terms of how this particular work can be leveraged further into solving the requirements of surrogate workload. And then so basically in short, this also showcases how we are also trying, so apart from contributing to oneDNN, how we are trying to bridge HPC and AI by not just identifying bottlenecks, but also by solving them in open source frameworks to accelerate the global innovation ecosystem, and connecting both the worlds, which is the engineering side of designing the stack as well as applying it in AI for science. Now, I would like to take you to the next slide. This is again continuing with what I covered previously. And in this slide, we would like to discuss about how we have contributed to oneDNN kernel. So in order to give a background of this particular slide, you can look at the representation over here. When we look at Perf, one of the critical performance libraries for AI workload, as we know, is oneDNN. And our team has been contributing to oneDNN for last many years. And when I started off, I also mentioned about how this work was a part of the Fugaku supercomputing project as well. Now, recently, our focus has been on Int8, MATML, and the BRGEM kernels, which are vital for inference speed on AI surrogate. So through specialized JIT kernel and thread composability, we actually achieved a remarkable improvement, which is like 35x, as you can see in this graph. So 35x performance boost and about 1.6x speed up and optimized weight reorder. So what does this mean? So it basically means that we were able to achieve significantly faster runtime for quantized inference, which is essential for deploying efficient scientific ML surrogate models on ARM-based HPC systems. And beyond performance, these contributions also directly strengthen the UXL ecosystem, thereby connecting open source kernel innovation to real world AI workloads. And I think as a part of the UXL Foundation initiatives, we need to connect the application domain with the way we are able to accelerate and bring in innovations in the oneAPI stack, and that is what we tried to touch upon. Now, after my talk, we have a talk by Ashish and Shreyas from my team, and they'll be sharing further details on the idea that I've shared in this slide. And I think they'll be talking on how they are accelerating DL on ARM through oneDNN. So there'll be a detailed presentation on this aspect, so I'll skip that. Okay, so with this, I would like to slowly converge the message that I wanted to put in, as well as my talk during this summit. So as a company, we believe in collaborating with the global community and bring in this open source touch to the way we are contributing to the accelerator ecosystem. And presently, Monaka team basically collaborates with ARM, Linaro, UXL, Supermicro, AMD, and with Monaka X, which is the next project that we are going to be glued in. We also have a partnership with NVIDIA when it comes to using it from GPU ecosystem perspective. So as a concluding remark, yes, our vision is to align software acceleration commitment with green data center goals. And we basically, aim to democratize AI for sustainable digital transformation. And with this, we have been contributing, really well, I'll say, or exhaustively to various stacks of UXL, thereby accelerating these stacks for ARM ecosystem, because that's our major focus area, and thereby also enabling it for variety of other applications, including scientific ML and AI surrogate model. And we'll continue to contribute and collaborate in this ecosystem. And yes, we welcome feedback and contributions from everyone who is attending the talk, as well as the community on how further they would like to see us collaborating to AI for science, as well as the oneAPI stack. These are some of the resources, and all of them, we have just linked some of the successful pull requests and references that I have used for preparation of this talk. And if you want, you can visit this sites. We have QR code for each of the sets out here. And that's it. Before I end the talk, I would like to acknowledge and mention that the project we are basically contributing to is based on results that is obtained from a project which is JPNP 21029, supported by New Energy and Industrial Technology Development Organization, NIDO, from Japan. Thank you.